back to the studio. Today, we're unpacking the core logic behind almost every modern app you use, object-oriented programming in Java, or OOP. To understand why we need it, imagine trying to build a smartphone, but all you have is a massive pile of raw microchips, loose wires, and glass dumped on a table. If you write a large application as one giant, continuous list of instructions, your code looks exactly like this tangled mess. It's incredibly fragile, and finding a single bug becomes an absolute nightmare. Object-oriented programming prevents this chaos. Instead of a single messy pile of instructions, we organize our software into neat, self-contained modules that behave a lot like physical objects in the real world. A 2D smartphone blueprint is a class in Java. It defines the phone's capabilities, but isn't a physical phone. As this blueprint extrudes into solid 3D shapes, we get a working object. One blueprint can build millions of physical objects. Writing Java this way means building your software out of these distinct, manageable objects, rather than writing a single, fragile script that can easily break. To keep these objects organized, Java relies on 4 structural pillars. You can remember them with a simple memory trick: EIPA. The E stands for encapsulation. This is the practice of bundling your data together and strictly restricting direct outside access to it. Think about your phone's battery. The manufacturer seals it tight inside an unopenable case. They do this specifically so you don't accidentally tamper with the raw power cells and destroy the entire device. If you want to interact with that battery, you can't touch it directly. You have to go through a specific, safe, controlled channel, the charging port. This image shows exactly how that looks in Java code. We use the word private to hide the sensitive battery data, and we use public methods to act as our safe charging port to modify that data. Next is the I, which stands for inheritance. This allows one class to absorb the properties of another class, giving us massive code reuse. When a company releases a new Pro model of a phone, they don't invent a completely new device from scratch. They take the base model's existing design, keep what works, and simply snap on extra features. This layout shows the Java syntax for that upgrade. By typing the word extends, the new child class instantly inherits all the features of the parent class, without you having to rewrite the basic foundation. Encapsulation provides essential data security, and inheritance allows you to effortlessly extend existing code. Together, they make the foundation of our program both safe and highly efficient. The P stands for polymorphism. This translates to many forms, and it means the exact same instruction can trigger entirely different behaviors depending on the context. Picture the volume button on the side of your phone. If you press it during a phone call, it turns up the caller's voice. But if you press that exact same button while watching a video, it turns up the media volume. This animated diagram breaks down how that works under the hood. The first type is called method overloading. You use the exact same method name, but you feed it different inputs or parameters to get distinct results. Now the diagram shifts to show the second type, method overriding. This happens when a child class receives a behavior from its parent, but completely rewrites and replaces that specific behavior with a new, distinct action of its own. Finally, we reach the final pillar, A, abstraction. This is the practice of hiding complex internal details and exposing only the essential features to the user. When you want to open an application, you just tap a friendly app icon. That simple tap entirely hides the millions of complex circuit board calculations happening in the background to launch the software. In Java, tools called abstract classes and interfaces act just like that simple app icon. They allow developers to focus purely on what the object does, rather than getting bogged down in how it actually does it. Polymorphism gives your code the flexibility to adapt to new situations, and abstraction strips away the complex clutter, allowing you to scale your software smoothly. So, the next time you sit down to structure a piece of software, just remember EIPA, encapsulation to secure your data, and inheritance to reuse your code, polymorphism to add flexibility, and abstraction to hide the complexity. By combining these 4 pillars, developers can take raw, disorganized commands and assemble them into clean, functional, real-world digital objects. If this breakdown helped you see Java in a new way, drop a comment below. Please like, share, and subscribe for more tutorials, and we'll see you in the next video.